Hello, James Flaten here with the Minnesota Space Grant. Let's take a look at calculating how a rocket moves. First, let me share my slides. So I'm interested in calculating the motion of a rocket. And for simplicity, let's just talk about purely vertical flight. We won't worry about sideways winds or the fact that the rocket might drift. There's basically three phases, at least for a high power or a model rocket flight. The first phase is the boost phase, when the rocket is firing, the motor is firing. So the rocket is actually losing mass, but it's going upwards faster and faster, so it's accelerating in the upwards direction. Second phase is the coast phase, after the motor has burned out. So now the rocket isn't changing mass anymore. It's still going upwards, but it's slowing down. So it's accelerating, but in this case, it's accelerating downwards. And then the third phase is entirely different. The third phase is coming back down again, the descent phase. So there's a parachute deployed, the mass is fixed, it's going down at perhaps a terminal velocity, perhaps a constant rate. So acceleration in this case would actually be zero. Just to set up the physics of this situation, here are the variables one might use. X for position, height above the ground. Positive will be up. V would be velocity, the rate at which the position changes. Positive again means up. Acceleration A, that's the rate at which the velocity changes. And so if it changes more in the upwards direction, that would be a positive acceleration. Or if it changes more in the downwards direction, that would be a negative acceleration. T will be time. Now, if you've studied physics, you probably already know that if you have a constant acceleration situation, you can calculate your velocity at any time. V at time t would be equal to the initial velocity plus a times the time. Acceleration times the time. And the position at time t would be the initial position plus the initial velocity times time plus 1/2 acceleration times time squared, t squared. However, it turns out that rocket motion rarely has constant acceleration. So these particular equations have limited utility unless you use them for very small amounts of time over which perhaps the acceleration is constant, and then you redo the calculation over and over again, perhaps using a computer. You can make some progress though. So let's think about Newton's laws of motion, which say that forces explain motion. And if we can understand the forces, perhaps we can figure out what the motion is going to be. Here are the three phases. In phase one, we have the rocket, which has weight, thrust, which should be a much longer vector than that, actually, pushing upwards. Weight pushes straight downwards. Drag is opposite the motion, so drag in this case would be downwards also. And let's just assume that we're going straight vertically, so there is no lift, there's no sideways force. Phase two is just the same diagram, except no thrust. So the drag is downwards, the weight is downwards, but there's no thrust. And then phase three is completely different. Phase three has the weight downwards, but the drag now is upwards because the drag is opposing the motion, and in this case, the motion is downwards. So here are some comments. The gravitational weight, that would be W, points directly downwards toward the center of the Earth, and thrust points forwards. In other words, it points in this direction of the rocket body, which we'll assume is straight up. But that's only for the boost phase. Drag always points opposite the motion, so typically that points down the rocket when the rocket is moving up, and upwards when the parachute is deployed and the rocket is moving down. And then any sideways forces would be technically called normal or perpendicular forces or lift forces. For this calculation, we'll just assume those are zero. If you sum the forces, if you add them together as vectors, okay, you use the Greek letter sigma, and Newton's laws tell us that if you sum the forces, that will be related to the mass and the acceleration. So here's Newton's first law. If the sum of the forces is zero, we sometimes say the forces are balanced, then there is no acceleration, so the velocity is constant. The thing will continue in a straight line at a constant speed, okay? Newton's second law is perhaps the more interesting one. Newton's second law says, if mass is constant, for instance, if you sum the forces, they can explain mass times acceleration, or perhaps written, a better way to write it might be acceleration can be explained as the sum of the forces divided by the mass. People sometimes say F equals ma, but they really mean it's sum of F equals m times a. Newton actually wrote this as changes in momentum, which allows the mass to be changing, and that might be more useful for rocketry. Newton's third law basically says that when two things interact, they push on each other, they pull on each other, both of them get forced in the opposite direction from one another by the same amount of force. But since it's two different objects being forced, these forces will never cancel out. So let's just take a look at phase three. Phase three is the simplest of the three. So in this case, we have an upwards drag force and a downwards weight, and they will in fact balance. So here's a free body diagram, which shows a mass. It shows an upwards and downwards force. The acceleration is 0. Okay. And so the weight, the downwards force W, can be calculated as m times g. G in this case is the gravitational constant associated with the Earth. So that would be 9.8 meters per second squared in the metric system, 32.2 feet per second squared in US customary units. This is the rate at which something would accelerate if you just let it fall freely. Now, drag is to be calculated based on the density of the medium through which you're traveling, air in this case, 1/2 times rho is density, times the velocity squared, times the cross-sectional area of the object, in this case the parachute, so I'll call that A sub p, and then a coefficient that describes how effective the parachute is, a drag coefficient. So let's call that C sub d, drag coefficient, and then p because it's a parachute. So here V sub t would be the terminal velocity, A sub p would be the cross-sectional area of the parachute, and C sub dp would be the effectiveness of the parachute, typically a number between 1 and 3. You can look up that number. It depends on the geometry of the parachute. And the density of the air near the surface of the Earth is, well, it's given there, 1.2 kilograms per meter cubed, or in US customary units, it's a little bit stranger. Okay, so if I apply Newton's second law, which basically says D, which is the upwards drag force, minus W, the downwards force, which is supposed to be then equal to m times a, but a, acceleration in phase 3, is 0. So that means D and W must balance. They must be the same size. One is up, one is down, okay? And W is m times g, and D can be written as 1/2 rho p squared times a times c. So for instance, one could imagine taking this thing, and since you know things like the density of the air, you know the weight of the rocket, perhaps, you know the area of the parachute, you could potentially solve for the speed. In other words, this tells you how does the speed depend on the weight and the density and the area and the effectiveness of the parachute. It's the square root of 2 times the weight divided by the density divided by the area divided by the coefficient. Or if you have a specific speed in mind, you could potentially use this to calculate the area. In other words, to help size the parachute. Let me step out of these slides for a moment and just show you an example of the application of that first equation. So I'm going to go and share a different screen. There we go. So let's say I want to calculate the terminal velocity. Well, the terminal velocity is the square root of twice the weight divided by the density and the area and the coefficient. That's from the slides we were just looking at. And so in this case, the weight of the rocket would be the weight of the original kit plus the weight of the motor minus the weight of the propellant, because at this point the propellant is burned out. So for instance, for an example situation, you might have a 37-ounce rocket with a 10.5-ounce motor, of which 4.87 ounces was propellant. So you subtract that off, put it all together, and you come up with 52.37 ounces or 3.27 pounds. So that's the weight. The density of the air is equal to, well, this is actually probably a useful conversion to do. It's 0.0749 pound mass divided by cubic foot, but we can change that into 0.00234 pounds times seconds squared over feet to the fourth. That might be the more useful one. So the parachute area, let's say I have a 36-inch diameter parachute, but let's say there's a 6-inch diameter spill hole in the middle of it. So the area would be pi r squared for the big radius minus pi r squared for the hole. So that's pi times 18 inches squared minus pi times 3 inches squared. Put that all together and I get 990 square inches or 6.87 square feet. So that's my parachute area. The drag coefficient, let's just assume that this parachute has a 1.5 drag coefficient. Again, you can look that up. It's based on the geometry of the parachute. Put all this together and I come up with a terminal velocity would be the square root of 2 times 3.27, that's the weight. So we're talking about divided by the density and also divided by the area of the parachute and divided by 1.5, the coefficient. Put that all together and I have the square root of 407 feet squared over seconds squared, which is handy because when I take the square root of 407, I get 20.2. And when I take the square root of feet squared, I get feet, and the square root of seconds squared, I get seconds. So ultimately the answer is 20.2 feet per second. Those are good units. And in fact, that's a reasonable number. I want the value of the descent to be something perhaps less than about 25 feet per second, so I don't break the rocket when it hits the ground. So this is a reasonable descent speed. Okay, let's go back to my other slides. That was phase 3. That's the easy one. Let's take a quick look at phase 2. So in phase 2, we have the weight and the drag. They're both pointing down. There is no thrust in phase 2. Okay. And so in this case, the free body diagram shows two forces. They're both down, and there is clearly an acceleration. It's down. Okay. The weight is calculated as mg, just like before, and the drag is calculated as 1/2 rho v squared AR, where AR now is the cross-sectional area of the rocket as you look at it end on. So that's probably a pretty small number. And then the drag coefficient for the rocket, which also, well, that probably won't be the same sort of number as the drag coefficient for a parachute. Okay. So in this case, the speed as the thing is traveling upwards with its coasting will diminish and eventually it will reach 0. If this is a streamlined rocket, I kind of assume that its drag coefficient is pretty small. The density of air will still be 1.2 kilograms per meter cubed. And if I apply Newton's second law, we have this downwards drag and the downwards weight, and those are supposed to explain an acceleration. So clearly the acceleration for phase 2 will be downwards. And it turns out the drag is likely to be small because it's streamlined and gets even smaller when the velocity starts to get small. So notice that if we were to neglect drag altogether, it's a big if, but if we were to neglect drag altogether, then we would just say the downwards weight gives you mass times the acceleration. But weight is mass times g, and so apparently, if we neglect drag altogether, the coasting phase is just motion with acceleration downwards for the value of g. That's called free fall. Now, we could calculate, for instance, if you know the point, the height above the ground at which the rocket starts to coast, okay, let's call that x1. We could then calculate perhaps x2. That's the height at which the thing reaches a 0 vertical velocity. That's called apogee. So x2 would be x1 plus v1 times t, the duration of the coast, minus 1/2 g t coast squared. And since the velocity at apogee is 0, basically we can then calculate that this thing will coast for a time of v1 over g, where v1 is the speed at burnout. So that's actually the top speed of the rocket. And after that, all speeds are going to get slower and slower, and eventually it will stop going up after a certain amount of time. And you can calculate exactly how high that is if you want to. Okay, but that's only if drag is neglected, and that might not be a really good assumption. On the other end, if drag is not neglected, then this is not a constant acceleration situation at all. And so difficult to use this particular equation. Let's take a look at phase one. So phase one is the same forces, except now we have an upwards thrust, which will exceed all the other forces because it's going to be accelerating upwards. Here is a perhaps pseudo-realistic force diagram, a downwards drag, which is getting bigger and bigger as the speed increases, a downwards weight, which is getting smaller and smaller as the mass decreases because the rocket motor is burning mass, and then an upwards thrust. And the upwards thrust due to the motor might not even be constant in time, depending on the type of motor you're using. So it's actually very complicated. We can do a little tiny bit with this though. The largest thrust is T, and although it's not constant in time, it might be predictable. You might have a thrust curve, for instance, that tells you, yes, the thrust is high at first and lower later, or perhaps it's fairly level. Okay. The rocket mass changes. It goes from the full loaded mass, call that M0, down to the empty mass of the rocket. So the empty mass, M1, is M0, well, M0, the total mass is equal to M1 plus the mass of the propellant, okay? So the idea is the difference between those two masses is the propellant, which is going to get burned. At any moment in time, there's a specific weight, and the weight is m times g for that moment in time. And then the drag is increasing as the speed picks up, and it's always calculated as 1/2 rho v squared times AR, the rocket cross-sectional area, times c, the coefficient drag of the rocket itself. And again, CDR might be fairly small because this is a streamlined rocket, and the density of air will be the same number that's been used before. Unfortunately, if you try to apply Newton's second law, the sum of the forces equals T, the thrust upwards, minus D, the drag downwards, minus W, the weight downwards, equals M times A, but T is changing in time, and D is changing with speed, and W is changing as you burn fuel, and mass is changing as you burn fuel, and so the acceleration is definitely not going to be a constant here. So there's, again, not that much utility in this specific equation unless you apply it for just tiny pieces of time and then do it over and over again with a new acceleration every time. So this is not constant acceleration motion, so the calculations become difficult. I guess this is why they call it rocket science, right? Okay, let's just take a look at another approach altogether. Okay, this is sort of a sideline. You can think of thrust as sort of two things. One thing is the momentum exchange between the rocket and the exhaust. So the idea is you push exhaust out, and so the exhaust pushes back on you. That's momentum exchange. But it turns out that a part of the thrust that you get is also related to the pressure imbalance. You have a high pressure exhaust, and then you have an environment which is at a different pressure. And so this part of the thrust, in fact, makes a big difference whether you're near the surface of the Earth or in outer space. Because near the surface of the Earth, you have an environmental pressure, which is atmospheric pressure. And in outer space, the environmental pressure is 0, okay? And so the amount of thrust you get is momentum exchange plus pressure imbalance, but the pressure imbalance depends on where you are. Okay, that was just a side note. I'm not going to go anywhere with these particular calculations, but I just wanted to point that out. Let's take a look at a thrust curve. So here's a thrust curve for an H125 motor from Cicerone. A thrust curve is a curve that shows how much thrust you get at different times. So in this particular case, as time goes by, I notice over on the right-hand side, I have about 2 or 2¼ seconds. So this motor will burn for about 2 seconds or so. And notice, if I look vertically, this is the thrust in newtons, and notice the thrust is not constant. It goes up to 140 newtons right off the bat, and then it settles back down to less than 100 newtons, and then it sort of gradually climbs up above 150 newtons in the middle. That's at about 1 second in. And then it slowly decreases to around 130 newtons, and then it drastically falls off. Basically, the motor is burning out, okay? So what we're going to do is we're going to call the beginning of the burn time the 5% of maximum level. So the start time here is labeled on the left-hand side as just a little bit to the right of 0.00, so maybe 0.05 or something. And then the end time, just a little bit more than 2 seconds, also dotted line, okay? That would be when the thrust is now fallen below the 5% level, 5% of the max. And although the thrust goes up and down within the start to end time, you could imagine having an average. So the average thrust with the dotted horizontal line is just above 130 newtons. In actuality, considering this is an H125 motor, it probably should have been more like 125 newtons. So there might be a slight error in this diagram. But basically, the impulse is the area under the curve. And so you can either calculate the area under the funky curve, or you can just determine the start and end time, the average thrust, and multiply those two together to get the area of the box. And that's what an average means in this case, is how can you box this up so that you get the same area as the funky curve. There's maximum thrust, there's the 5% start time, the 5% end time, or the burn. That's the burnout time. And so the total duration of the burn is between those two. Average thrust will be this line. Impulse is the area under the curve, or burn duration times average thrust is another way to calculate it. There's the initial spike. Not all motors will have that. A progressive motor or a progressive part of the burn is when the thrust is increasing with time. Regressive is when thrust is decreasing with time. And if you had something where the thrust didn't change at all with time, we would call that a neutral burn. Okay, so here's some vocabulary. Now, motors are classified based on their impulse. Sometimes I refer to that as how much energy, how much fuel you have, but in fact, this is the technical definition. And so from 160 to 320 newton seconds, that would be an H motor. From 320 to 640, that would be a I motor. From 640 to 1280, that would be a J motor, etc. And if you want to fly these motors for high power, you need level 1 certification to fly H and I motors. Level 2 certification gives you access to JK and L motors, etc. We were just talking about a Cicerone Pro 38 266 H125-12 motor. Okay, usually called just the Cicerone H125. So this is the manufacturer. This is the diameter in millimeters. There's the total impulse, 266. So if I look up, 266 is within the H class. It's between 160 and 320. It's 266. It's kind of mid-range in the H class. H is the impulse class, so that's another way of talking about impulse, but it's less precise than the 266 number. 125 is the average thrust in newtons, and the 12 is the built-in delay time, and you perhaps can adjust that, at least on some motors. It turns out that somebody figured out back around 1900 a specific equation called the rocket equation. And this rocket equation helps you figure out, if you know the impulse, how fast you can actually how much speed you can pick up using this motor. Okay, so the impulse is the area of the thrust versus time, area under the thrust versus time curve. Okay, or you can essentially calculate that as the thrust average multiplied by the burn time. And then you can define ISP. So ISP is specific impulse. The specific impulse tells you basically how effective, how much impulse you're getting per propellant that's gotten burned. Okay, so ISP is defined as the total impulse divided by the weight of the propellant that was burned, mg, where m in this case is the propellant mass. So total impulse divided by mg, that's called ISP. Typically, this is a number in the vicinity of 200, maybe a bit less than 200, maybe a bit more than 200, and the units are actually seconds. Okay, so here is the rocket equation. The rocket equation says you can change your velocity, ideally, as much as ISP times g times the natural logarithm of your initial mass over your final mass. And if you happen to start from 0, then the change in velocity will just be the final velocity. So in this case, the final velocity is ISP times g, the gravitational constant, times the natural logarithm of m0, that was the full loaded rocket, divided by m1, that was the rocket after its fuel had been burned out. Now, this is ideal case if nothing is resisting you. It turns out there are some things that are resisting you typically. For instance, drag will resist you if you're flying through the atmosphere. If we even ignore that though, in our case for a vertical rocket launch, gravity is also resisting us. We have to climb uphill. And so typically you won't get going this fast. Remember, V1 is the maximum speed. It's the speed at the end of phase 1. And you won't in fact get going as fast as this. You have to subtract off how much of that speed got taken away by gravity. So that's called a gravitational penalty. So the gravitational penalty equation at the very bottom here is V1 is equal to ISP times G times log of M0 over M1. That's what we had before. But we need to subtract G times the burn time, or G times the time of the phase that we were in. We're in phase one. So this is sort of the maximum speed that can be achieved. And it's easy to calculate. You just need to know the ISP of the motor, and you need to know the mass, fully loaded, and the mass after you finish burning your rocket. And you need to know the burn time of the motor. So that's actually pretty slick. Here are three motion graphs. Acceleration versus time. Typically, if you have a rocket flight, first you have burning, so you have significant positive acceleration. And then during coasting, your acceleration might actually be negative because you are slowing down, gravitationally slowing down, even if you ignore drag. And then once the parachute is out, the acceleration is basically zero. You're not changing your speed anymore. Velocity in the middle there increases to a very high velocity and then slowly diminishes. And then once the parachute comes out, the velocity goes negative. It might be a fairly constant number. And the altitude versus time increases until you get to apogee. Apogee is when the velocity is zero. And then after that, the altitude slowly decays away as you come down under parachute. So here are three typical graphs. Often these graphs are drawn superimposed upon one another. So you just have to be careful. So let me just point out that you can see phase one, that's the boosting time, the positive acceleration time. You can see phase two, that's the coasting time. That's the diminishing velocity time, or the negative acceleration time. And then you can see descent time, that's the zero acceleration time, or the negative velocity time. So by looking at these graphs, you should be able to check when does burnout occur, when does parachute deployment occur, what would happen if you were to change something like increase the delay of the parachute deployment by some number of seconds, maybe not have it come out of apogee. Here's my last slide, and this just shows similar things to that last graph, except they're all drawn on the same grid, which can be confusing. So you have to pay close attention to the axes and to the units. So in this case, I see the main line that's in the middle. I'm not sure if you can see my cursor. If you can see my cursor, I'm circling it, but if you can't see my cursor, the curved line that is curved over and it's labeled apogee 3060 feet above ground level or above level ground, okay? That is the altitude line, and it uses the left-hand axis. So the left-hand axes say altitude above ground level, 500, 1,000, 1,500, 2,000 feet. Okay, so this thing just barely gets above 3,000 feet and then starts to come back down. And then notice it comes down relatively slowly, perhaps at a rate of 20 feet per second. So apparently it's coming down under parachute. And after 60 seconds, that's when this graph ends, it's still above 2,000 feet. So in other words, this graph doesn't show it go all the way to the ground. That part of this graph is the altitude shape. However, on the same graph, on the left-hand side, you have this very high vertical sort of triangular spike, okay? That's the velocity. And the velocity numbers are to be understood as feet per second using the axis on the right-hand side. So notice that that very sharp spike goes slightly above 500 on the right-hand side. So this means that this rocket starts from zero velocity and picks up speed to about 500 feet per second. And then it starts to coast. And as it coasts, the velocity drifts back down, back essentially to zero, and then ends up slightly negative as it comes down under parachute. That isn't, in fact, shown on this graph. But I see the maximum velocity, Vmax, is about 550 feet per second. So using the right-hand numbers with units of feet per second. On the other hand, the same graph is going to use the right-hand numbers. This is confusing, but the right-hand numbers for acceleration as well. And so that would be in G's, in numbers of this G constant, where G is the free fall gravity constant, okay? And so that's actually a very small thing. It's right down in the left-hand corner, and it shows that the acceleration goes up to about 25 Gs, stays there for a very short time, only less than 2 seconds. And then after that, the acceleration basically is pretty much slightly negative, 1 G negative, perhaps during coast, and basically zero on descent. So that is also not shown. So again, the acceleration is going to use the numbers on the right-hand side, but use them in a different unit altogether. So You gotta keep your wits about you when you're taking a look at this graph. I would not, in fact, recommend drawing graphs this way, but essentially all the programs that do simulations will superimpose all the things on top of each other. So you have to be used to reading graphs that look like this. That's what I've got. So again, these are calculations for rockets that go straight up, don't drift sideways, burn for a time, coast for a time, come down under parachute at basically a constant rate. And since these things aren't really constant acceleration phases, it's challenging, not impossible, but challenging to use Newton's three laws. But if you use computers or use simulation programs that calculate things by little tiny increment time steps, you can use Newton's laws. Or you can use something like the rocket equation, which tells you if you know overall total masses, know overall ISPs, for instance, then you can calculate how fast you will go, at least at the end of a burn.